to find an invariant showing the class of topological equivalence of conjugacy means to get the topological classification for this class. Here we study the Morse Smale flows on surfaces. A flow on surface is called Morse Smale if its non-wandering set consists of a finite number of hyperbolic fixed points and a finite number of hyperbolic limit cycles. And there is no trajectories connecting saddle points if we speak about surface. And here is an example of a phase space of some simple Morse Smale flow on a sphere. Here is 4 fixed points and 2 limit cycles. Such flows have been classified topologically for many times. A few most important invariants are the scheme of Leontovich-Meyer for flows on the plane, the Peixoto's directed graph for flows on any closed surfaces, and the Ashemkov-Charcot molecule for also flows on any closed surface. So all these invariants classify flows only in sense of topological equivalence. And if we want to come to topological conjugacy, we need to recall what is moduli of stability. So if we consider a flow near a separatrix connecting saddle points, such rotation is not possible in our case, but in other class of flows this is possible. If consider such rotation, then you can find that in a class of topological equivalence of a flow, there is infinite many classes of topological conjugacy, and each topological conjugacy class is can be described by a modulus, a modulus of stability, which means some analytic parameter. Here, in this situation, it is equal to the ratio of eigenvalues of these saddles, lambda and mu. So such situation is not possible in case of Morse Smale flows, but there is a question, maybe some other situations give moduli in our class. First, in our previous works, we found that Morse Smale flow without limit cycles have not moduli, and its classifications in sense of equivalence and in sense of conjugacy coincide. But any limit cycle obviously generates a modulus equal to its period, because if you want to conjugate a flow on the limit cycle itself,
Vlad, what does mean modulus of limit cycle?
Modulus of limit cycle, it's period, of course.
Yes, but you introduce modulus for this picture with 2 saddles. No,
the 2 saddles. Yes, I mean that modulus is any analytic parameter which is invariant for the class of topological conjugacy and which describe this class. So for the situation with 2 saddles connected by a separatrix, it is a ratio of eigenvalues. For a limit cycle, it is its period. Yes. Okay.
Okay.
So there is 2 main problems of this work: is to find the criterion of the moduli finiteness for the surface Morse Smale flows, to find which other situations give moduli, and maybe in some cases there are infinite many moduli, and to classify the class with finite number of moduli. So let us recall that near fixed point, a Morse Smale flow is topologically conjugate with a linear flow with fixed points of type sink, saddle, and source. So, this follows from the hyperbolicity of the points, and the hyperbolicity of Libet cycles give us the fact that cycles can be only stable or unstable, and the neighborhood of a limit cycle is only annulus or the Möbius band. So let us look to the neighborhood of limit cycle and try to linearize the flow near limit cycle. If we consider a flow on the plane like this, on the left, with the vertical trajectories directed up, and if we introduce the homomorphism G mu lambda t by this formula, and the group of its action, and to glue the plane the way which is described here, we can get in two cases cylinder with a stable limit, cylinder with flow with stable or unstable limit cycle, or Möbius band with a stable or unstable limit cycle, and such flows are topologically conjugate with the Morse Smale flow on surfaces near its limit cycles. This is the fact proved by Irwin. And also there is a situation that gives us moduli, for infinite moduli for this flow, for Morse Smale flow. If we consider on the plane, if you consider, first we consider such situation when two cycles have a trajectory which goes from one cycle to another one, and consider image of horizontal lines on the plane and taken to the cylinder and then to the surface. We would find that there is modulus, functional modulus, because such image of the foliation consisting of horizontal lines on the plane gives invariant foliation, unique one-dimensional foliation near any limit cycle. Maybe it wasn't completely clear. Once more, let us take on the plane horizontal lines, then they can be projected to the cylinders or Möbius bands, and if by means of conjugation homomorphism we take this foliation to the surface back to the surface, then we can find that by means of conjugacy there is unique foliation near limit cycle. So this gives us functional modulus if two limit cycles have a trajectory going from one cycle to another one. So from this we get the property when the criterion when the Morse Smale flow have finite number of moduli. So Morse Smale flow on a surface has a finite number of moduli if it has no trajectory going from one limit cycle to another one. So one problem is solved, and all we need is to get topological classification in the sense of topological conjugacy. Let us call by G the class of Morse Smale flows with a finite number of moduli, and let phi t is a flow from this class. Here we use ideas by Roshenkov-Sharkov, and our ideas which we were using when we classified flows, omega stable flows, in sense of equivalence. Let us choose around each limit cycle some neighborhood. I will better show here on the picture. Here is the same example of Morse Smale flow, and here is two cycles, limit cycles, and the two neighborhoods, a neighborhood near each cycle is chosen. So the boundary components of these neighborhoods divide the surface into the so-called elementary regions. Here there are 5 elementary regions: this green, blue, red, blue, and green. So Morse Smale flows can have elementary regions of 3 types: a region of type L with a limit cycle inside, a region of type A with a source or sink inside, like these green regions, and a region of type M with at least one saddle points and maybe other fixed points. Of course, in general case of Morse Smale flow, there is 4th type of elementary region without any fixed points or limit cycles, but this type of elementary region is prohibited because it gives us an infinite number of moduli. So let us introduce the directed graph from which we begin to construct the invariant. This is a graph whose vertices bijectively correspond to the elementary regions, and the edges bijectively correspond to elementary regions, to boundary components of elementary regions. So here is the graph with 5 vertices and 4 edges, and edges are directed in the direction of moving along trajectories, because each boundary component is intersected by the trajectories, and so we can choose a direction of an edge corresponding with the direction of moving along the trajectories. But of course, this graph is not consist enough information about the conjugacy class of a flow. So and by the way, there is some proposition about properties of the graph. Each M vertex can be connected only with L vertices, and with every L vertex only by a single edge. Every A vertex can be connected only with L vertex by a single edge, and every L vertex has degree 1 or 2. If its degree is 2, then both edges either enter the vertex or exit. So by this graph, we already can tell which type of the cycle is, because if the edges are directed to the vertex, then the cycle is a stable one. If they directed otherwise, then it's unstable. If the L vertex has is incident only to one edge, then the cycle have a neighborhood the Möbius band. If it is incident to two edges, then it is on the annulus. Also, we can tell which point lies in A region. If edge is directed to it, then this is sink, and in other situation this is source. So you can look at the picture again. All this is visible here, but which we cannot tell by this graph what happens with this M region, and we don't have any information about modulus of the cycle. So we equip L region with the period of the cycle. We equip L vertex with the period of the cycle which lies in the corresponding L region, and for M region we construct three-color graph. How we do it? Because in M region situation can be very, very complex, very complicated. So in this case, no, of course, the flow can not have any limit cycle. Then the whole surface is the M region. But in other situation, the M region is a surface with edge. It have some number of holes. And here at the example, the M region have two holes, and we attach to each hole the two discs, and we introduce the flow F T such that it coincides with the previous flow on the M region, and have a sink there where phi had a stable cycle, and it have a source where where was unstable cycle. So here is the first flow and the second gradient-like flow without limit cycle constructed by the first flow. So here is unstable cycles, here is source, here is stable cycle, and here is sink. So
Vladislav, you have 5 minutes.
Only 5 minutes, thank you. So let us take away all invariant manifolds of the saddle points, closures of all separatrices of the saddle points, and the connected component of the set which we get in this case is a seal, which contains a single sink omega and a single source alpha in its boundary, and the whole seal is the union of trajectories going from source to sink. Then in each seal we take away some usual trajectory going from source to a sink, and call this trajectory by T curve. And the connected components of the set which we get in such case is the so-called triangle region introduced by Oshankov-Sharko. It have 3 sides: a stable separatrix of a saddle, unstable saddle separatrix, and the T curve. it is homeomorphic to an open disk, and this I already said, which is written in this proposition. We construct three-color graph by the next way. Each vertex is correspond to a triangle region, and each edge is correspond to the sides to a side of a triangle region and have a corresponding color. So here stable separatrices are green, and the corresponding edges are also green, and so on and so forth. Then we equip the M region with a three-color graph of its by a three-color graph of the corresponding M region, and also we equip edges which goes from goes to limit cycles with a cycle. I mean that I forgot to tell that each source and each sink correspond to some color cycles on the three-color graph. And as we exchanged limit cycle to a source or a sink, then each cycle near M region have corresponding color cycle of a graph. And so we equip our directed graph by three-color graphs, by period of cycles, and by color cycles which can tell us about the direction of limit cycles, because it is very important for the equivalence to preserve the information about direction of limit cycles. So two flows are topologically conjugate if and only if their equipped graphs are isomorphic. Thank you.
Thank you very much.
What difference between your graph of conjugacy and Oshenkov-Sharkov graph? It is two dual graphs or not?
The main difference is the equipment of the periods of the cycles.
Yes, in your class, there are no trajectory connection between limit cycles, okay?
There are no, but the periods of the cycles are necessary to describe the conjugacy class. But it only moduli here which are needed to
different.
Describe.
You need modulus, yes. Okay.
Yes, the periods of the cycles.
Okay.
But the result is that there are no other moduli. And also this graph is a bit different of the Oshenkov and Sharkov's graph, because they equip in different way and divide the surface in different way. They choose the neighborhood near any node point. They introduce a vertex for any node point, and we with Olga Vitalyna decided that it is not necessary. Only if a source or a sink lies inside a disk bounded by a limit cycle.
Mm-hmm. Okay. Mm-hmm.
Without any saddle points.
Mm-hmm. Okay.
Mm-hmm.
Еще, пожалуйста, вопросы задавайте. Так.